Good morning, everyone. My name is Mike Gualtieri, Principal Analyst at Forrester. I cover big data and data science. So that means I cover all the big data platforms, such as Hadoop. I do the Hadoop Wave, co-author of the Hadoop Wave. I do the predictive analytics and machine learning solutions wave, streaming analytics wave. So a lot of platforms that have to do with data and machine learning, AI. And this is the business track, so I'm not going to get in too much detail, but I do want to go over the trends and the business impetus that we're seeing for AI and what's possible for data. There's a lot of hype out there about AI. So all of our research is focused first on, well, what are the business drivers? You know, why are companies even adopting technology? And we can see from this survey, which we do all the time, and it comes out the same: customer experience, improve products and services, reduce costs. Those are very typical business drivers. So when we look at these technologies, it's in light of those business priorities. Now, the number one priority, and has been this way for a few years, is what we call hyper-personal real-time relationships. And you've heard this in the keynotes, you hear it everywhere, right? Companies want to create these hyper-personal real-time relationships with their customers, and we can do that now with data and machine learning. And what that means is that you can build applications that have information to help customers, simplify things, even make applications that maybe seem a little more emotional, anticipate your needs, and also engage with customers in natural interfaces. But to do this, how do we create these hyper-personal interfaces when we have millions of customers? Well, I call this, the friend factor. Because to do this, customers want and increasingly expect you to know them as well as friends. How else could you possibly anticipate their needs, understand them, make them smile, feel them better about your organization? The problem, though, with thinking about your customers as friends is that we as humans have a limit. And that limit, it's a research-based limit, is 150. And that means we can only have 150 stable relationships at most. And this is Robin Dunbar, University of Oxford, who has done this study. And even in the age of Facebook, we can only maintain 150 stable relationships. So he developed this thing called the Dunbar number, and it's the cognitive limit to the number of people whom one can maintain a stable relationship, friends, right? Now that limit extends. For example, his research showed that we can recognize about 1,500 faces. So that's why you can recognize Axl Rode, by face, because we can recognize a lot more faces, but we can only have those relationships. So that's sort of a conundrum for companies, because how can you maintain all those relationships? So what companies are trying to do is they need to be friends, or they need to treat them like friends, but they're trying to take it one step further with what at Forrester we call the age of the customer. I call it celebrities. And that is, how can we treat each and every one of our customers like celebrities? Now, if all of us go to the Cheesecake Factory, say, we're all going to get the same exact menu. That's not very personal. That's not how a friend would engage us. But if George Clooney went in, it would be a customized menu. Prosciutto would be front and center. They'd interface to his Fitbit, and they'd only display the Kahlua cheesecake if he worked out that morning. So companies are trying to create these celebrity experiences, and to do that, they have to learn the individual customer characteristics and behaviors. They have to detect those needs in real time and then adapt those applications in real time to serve the individual needs of the customer. The problem is 150. We, as individuals, can't scale beyond 150 relationships, and companies have millions of customers. So how can we create these hyper-personal relationships, but at the same time scale those to an individual level? Well, we can't using existing technology, and that's sort of the impetus for the use of artificial intelligence in organizations. Now, we did a survey last year, and we actually asked people, this isn't necessarily companies doing AI, but what is the biggest strategic growth benefit of AI will contribute to their organization? And it aligns with the business priorities to improve the customer experience, to improve products and services, perhaps even to disrupt an industry. AI is also on the syllabus 3 years ago, big data was on the syllabus, right? That was the hot thing that business schools were teaching. Now it's AI. And I met this gentleman here who even has a title, Senior Machine Learning Engineer and Predictive User Experience. So again, combining machine learning and user experience in one role. And if you think about user experience design professionals, they don't know anything about AI. So we have to put those two together. Now, everyone asked the question, well, what is AI? Here's how we think about AI. There's two types of AI. There's pure AI, and that's about artificial intelligence, software systems, all aspects of human intelligence. That is not what we're talking about, and that's not what enterprises can do. Some of you might recognize this gentleman, Marvin Minsky. He was a co-founder of the MIT AI lab way back when. And in 1967, he said that within a generation, the problem of creating artificial intelligence will be substantially solved. And he was talking about pure AI. And that hype created the AI hype in the 80s, which crashed and burned. And that's not what we're talking about there. And in fact, we're no closer to pure AI. That's not what we're talking about. Bill Gates, he's concerned. And he doesn't understand why some people aren't concerned about superintelligence and AI. Well, Bill, the reason is because we're not close. We're still not much closer to the idea of pure AI than we were even back in the 80s, the 70s, or even the 90s. So what companies can focus on is what we call pragmatic AI. And pragmatic AI is very narrow in scope. So it's not about mimicking all aspects of human intelligence. It's about mimicking small aspects of it, like image recognition or a prediction. But because AI has access to a lot more data, sometimes that narrow scope can actually exceed human intelligence, like the Go game, for example, and in some image processing. So Ginny Rometty's characterization of this is probably a little more pragmatic. It's to augment our intelligence, narrow in scope. It's going to extend the expertise and the scale of the organization so that we can go beyond the 150 friends, so that we can scale and personalize to millions of customers. So when we look at what enterprises are actually doing, and this is from last year, it's that same survey, you can see the number one activity that enterprises are doing with AI is researching it. Right? So 58% are researching AI, and only 14% are actually training a model. That's actually awesome if you're a company, because it means that, and if you're not doing this now, this is awesome because you're not behind, right? There's a big opportunity in this space. So pure AI, no. Don't even think about that. We are not close, no matter what you hear. But pragmatic AI, using building blocks, what we call AI technology building blocks, that's what's possible. So to understand what pragmatic AI is, you have to understand the building blocks. Now, this is a combination of technologies and specific use cases, but you can see things like deep learning and machine learning. We also have sensory perception, because that's a very important part of this as well. So now, when people say, I am doing AI, they may be saying, I am just doing machine learning and calling that AI. That's fine these days. Okay? They may be doing multiple of these in combination. Now, what we did here is we looked at these technologies and use cases, and we ranked them. Pragmatic 1, Pragmatic 2, Pragmatic 3. So Pragmatic 3 means it's more mature, okay, and you can do more with it. But the fact that they're in the pragmatic category means that they can be used now, and enterprises are using these technologies now. And you can use these to build that intelligence, the AI, into your applications, your business processes, your customer experiences. Now that begs the question, well, what is cognitive then? Cognitive is nothing more than pragmatic AI. It's a synonym. Okay, so when IBM talks about cognitive computing, you may notice nowadays they will also talk about AI. So cognitive computing is pragmatic AI, which means it consists of one or more of those building blocks. So we don't have to have any more conversations about what's the difference between cognitive, what's the difference between AI, nor do we have to have any conversations, or it's kind of awkward when I hear we want to do AI and machine learning. Because machine learning is sort of, it's underneath pragmatic AI, right? So that's the way to think of this. Now I'm going to walk you through some of those building blocks so you understand what your enterprise can do. And the first one is machine learning. So I'm going to try to demystify it for those of you who aren't familiar with the process. But when I think about machine learning, and when you think about machine learning, I always translate it in my head to prediction. Machine learning is about creating a model to predict something. Now, yes, there are machine learning algorithms that will find clusters and will find patterns, but even that is trying to predict something that's interesting. So when you think machine learning, think prediction. And when you think about scaling your customers, you want to predict something about those customers. So the definition of machine learning is that it's algorithms, and there's many. There's many categories of algorithms, GBM, support vector machine, random forest. There's a whole series of regression type models. But they're algorithms that find that model, that predictive model, that can predict an outcome with significant enough accuracy to be useful. So it's all a probabilistic model. So machine learning is about predicting. Now, if you think in your own business, well, what could I predict? You'll come up with dozens of things. We'll talk about that more in a second. So machine learning has been used for ages in telecom and finance, and other companies for that matter, to predict if a customer is going to churn. Is this customer going to leave? Because if you have a model that can predict out of your millions of customers that these 100 customers are 83% likely to leave, then, and you can do that ahead of time, you can take action on it, right? Netflix, a recommendation engine is built from machine learning models. Again, it's a predictive, right? Because it's predicting what shows it thinks you would like to watch. So ML equals prediction is the easiest way for you to think about what machine learning is and how it can apply to your business. But you have to understand that machine learning models, when they exist for what you want to predict, they're beautiful. They can be very profitable, and companies that have predictive models spend enormous amounts of time just trying to make them 0.5% more accurate, because if they're 0.5% more accurate, sometimes that leads into millions of dollars. But these models are always about probabilities. It's always about probabilities, not absolutes. And just because you wished you'd had a machine learning model doesn't mean that it exists in the real world. Look at models for predicting presidential elections. Look at models for predicting economy or stock prices, right? Some systems are just too complicated. I don't care how much data you have. You could have 1 trillion rows, but only have 3 columns, and maybe that's not enough data to actually find a model, right? Because you're missing some piece of data. And the other important thing is that machine learning models are based upon correlation, and they're probably not causative. Now what that means is that you can't just create a model and just deploy it willy-nilly. We'll talk about that later. And it also means you have to constantly monitor that model to make sure it still has predictive power for what you're trying to predict. Now, what would you like to predict about your customers? Well, maybe life events, certainly upsell, cross-sell. Many companies complain they don't have enough data about their customers, like about the customer record. Well, maybe you could predict some of those characteristics and then use those to be more personalized. So this just illustrates the point, because I don't want to get in trouble with data scientists. This is the most important point to understand, is that correlation does not imply causation. If you took a statistics class, remember, professor just kept saying this, right? So people do this all the time, especially politicians and economists. They'll give you one data point and they'll say, because of this, it equals that. Just know that the models that your data scientists create are based upon correlation, and they're probably not causative. Fundamentally, what machine learning creates, it automatically generates the model. It creates the code. So a data scientist actually is not really creating the model. The algorithm creates the model. The data scientist is kind of facilitating the creation of the model by applying the right algorithm and the right data set. But at its core, that model is simply a function. So if you want to predict 10 characteristics about a customer, How many models do you need? 10, right? So it takes some input variables, it creates a function which is in code, and then it predicts that outcome. That chunk of code can be deployed or called as a service. So once you create that model, that's how you can deploy it. So for those of you who aren't familiar with how this process actually works, I'm going to turn you into a data scientist in about 2 minutes, okay, if you understand what I'm about to say. So we're going to take a very simple use case, which is we want to create a model on whether or not we should play tennis. So here's the training data set. Now a training data set is always collected from the real world. So presumably we had a tennis pro go out there and look at the weather and say yes or no, we'll play tennis. So we've got the outlook, the temperature, humidity, and wind, and then we've got a historical data set that said yes or no to play tennis. So what we want to do as data scientists is we want to create a model, that function, which will predict yes or no based upon these conditions. Now, we could just like look at this table, right, and just say, okay, well, the weather, rain is cool, no. But what we want to do is we want to create a model for that. This is a small data set. What if it was, 1 million rows from, millions of customer transactions? So here's our data set. You got it? And here's what we do. We've got our data set there on the left, and then what we do is we take that data, this data here, and we take 70% of it and we put it in the training data bucket. We take 30% of it and put it in that test data bucket. Okay, so all we've done is let's just say we do it randomly. There are different techniques for doing it, but let's just say we randomly took 70%, we put it in training, and randomly took 30% and put it in test. Okay, now the machine learning algorithms, as a data scientist, you will pick an algorithm, pick one, support vector machine. You're going to run that algorithm against that data, and you're going to tell that algorithm, could you please predict the play tennis column? That algorithm is going to run through that data set, and this one's short, right? But it could be millions. That's why we need distributed architectures to run it on large data sets. And it will come up with a predictive model. It will not fail you. It will come up with a predictive model. The question is it accurate? So we've got our model, right, that we created no matter what. And then what we do is we run that model against the test data that we held back. It's called the holdback set. It's often called the test set. So we run it against that test set and to see how accurate it can predict the test set. If it predicts it with enough accuracy, we're cool. We're like, okay, it's 87% accurate. Maybe we're satisfied with that. Or it's 93% accurate. That's how it works. Now, what if it's 43% accurate? What do we do? Because that's not, well, it would never be 40% accurate. But what if it was like, it was random? In other words, the model did not work. Now what do we do? Well, we have two choices. We could try a different algorithm. We could say, let's just try a simple logistical regression. All right, we run that. No, we're still not getting anything. Let's try a, did we already try a support vector machine? Let's try a gradient boosted machine. Still nothing. Okay, so we still have failed. We have failed. We haven't found it. So now our second choice is going back to this data set and saying, you know what? We're missing some data. We must be missing some data. So what a data scientist will try to do is figure out if there's more columns to add or derivative columns to calculate based upon these columns. And then we'll run it again. And once we get that signal, once we get a model that's accurate enough, then we're cool. And that means that that algorithm turned this data into this model. Okay? Now, we as humans, it's a small data set, we could create this model, but this is what machine learning does. It's not always represented as a tree. Sometimes it's a formula or a calculation or a neural network. But essentially, algorithms and the right data turn that data into the model. So now you're a data scientist if you understand that process. Now another technology, one of the building block technologies that has gained momentum lately is speech. And you probably all use it on your phone with Siri or Google Now. It's pretty exciting because it's getting really good. But you probably also recognize that it's actually not that good, right? And part of the reason is it doesn't have contextual information. So you can try this later, but if you tell your phone, this machine can recognize speech, it will come up with this probably, okay? That's Amazon Alexa. But what if you said this machine can recognize speech, right? Because this machine too can recognize speech. So there's contextual information that speech has that prevents systems from understanding where we would understand because we have the visual context, right? When I say this machine can recognize speech, can you tell what I'm saying? You probably can't now, right? Because now you're saying, well, I don't know if he's talking about wrecking that nice beach or if he's talking about recognized speech. So there are some limits. Nevertheless, companies are making progress with this. A small company out of Austin, Texas, I believe, called Interactive Tell, they're using the Google Speech API to translate speech in real time to text while monitoring conversations at a car dealership. So anytime a customer or a prospect calls anyone at that car dealership, and it says, you're being recorded. But as that conversation is going on, it's translating that in real time and then doing an analysis of that conversation to determine if this is a sales opportunity, a customer service problem, and dozens of other potential problems. And it's doing it in real time. No data scientist necessary here because the APIs, Google has done it for you in this case. So that's speech. Now, another one of the AI building blocks that is also considered pragmatic AI is deep learning. And we have broken off deep learning from machine learning. So to us, it's a separate category. It's definitely a branch of machine learning, but it's kind of splintered off because it uses its own tools and it focuses on one particular technique, which is neural networks. And deep learning is the most exciting thing, new thing to come out. There was a breakthrough, you've probably all heard it before, but it was in 2012. And it's all based upon neural networks. We're actually a mathematical construct created, I think, in 1949, or at least in the 50s. It's a mathematical construct, but the computer science breakthroughs in 2012 had to do with two things. One is some shortcuts for training the model, finding the model, using the data, and also the hypothesis and proof that you could use GPUs to generate these models because they're very, very compute intense. So you saw NVIDIA on the main stage this morning, and for $129,000 you can buy this box, and it delivers 170 teraflops. So to train models in deep learning that used to take weeks can now take days and perhaps even hours. This is one of the most exciting things, but it also has narrow focuses because we're still not talking about pure AI. We're talking about very narrow focus. And in the case of deep learning, the most prominent use case is in image and video recognition. It's not the only one because actually speech recognition has been enhanced by it as well, but I'm going to talk to you about the images. Now, everyone talks about how deep learning can recognize images better than a human. Well, yes, on certain training sets, but here's a picture I uploaded to the Google API, and you can see here, 93% chance this model said there's a motorcycle in there. 88% it's a car. Do you see a car there? Maybe there's one. Maybe it is better. Maybe it's so far back we can't see it. But nevertheless, the top choice is a motorcycle, so that's good. Now here's another photo I put up, which is a little bit of a plane crash, non-fatal, but can you see the wing on the ground? How would you categorize this? Would you categorize that as wind sports? Probably not, right? Because we can see better than this model. This is Google's model coming back with this. Now, you might think that I'm kind of like down on deep learning. I'm not at all, actually. Because the reason why this image is not coming back, is because it wasn't trained to recognize air disasters or air crashes or air accidents. It wasn't trained. That's not the data set. It's because the way this works is an image is labeled, and if you don't have the labels, it's not going to learn. So I guess it's that whole thing, garbage in, garbage out, right? It still applies to deep learning, no matter how miraculous it is. But this is an opportunity for you, for enterprises, and I'll get to that in a second. So retailers are actually messing around with deep learning to recognize a customer's mood with facial recognition and facial expressions. Now you might think that, you probably heard the facial recognition is a certain ratio between the eyes and things like that. That's all been thrown out the door. Deep learning doesn't work that way, okay? So you can train these models to recognize emotion and expression with deep learning very easily. Now, another business case, which you hear a lot about, is medical imaging. MRI scans are increasing, but the number of doctors are not increasing. This is how many images there are in X-rays, CT scans, MRI scans can have thousands of images. So how do you scale that? Deep learning can be used to train models to be accurate and faster and less prone to mistakes. But look out on the internet when you talk about a certain model in deep learning, it's not about all medical images. It's about medical images, and I can create a model just to detect something about the lung, something about cancer. See, that gets back to the pragmatic AI, that it's very narrow in scope. If I wanted to predict every disease that's possible from an MRI scan, how many models would I need? I would need as many models as there are conditions, right? So it's good, it's really good, I love it, but that's the pragmatic aspect of it, all right? I don't want you to think that you just like throw a bunch of images at it and it just, can detect everything. Now here's the opportunity, say you're an insurance company, and I love this use case because this is beautiful. Insurance companies have adjusters. They take pictures of damage, lots and lots of pictures of car damages or buildings like this, and then the adjuster writes up a big old report, a detailed report of what the damage is and what it's like. It's very detailed, it has its own jargon. See where I'm going? So an insurance company might have 20 years worth of these images, okay? And they have all that cool labeling information to put through that model. So you could take an army of adjusters, maybe there were 1,000 or 2,000, and maybe you could reduce that to about 500 by automating the adjustment process, by taking pictures and having the AI analyze those pictures. Now, what if we wanted to do this for buildings and automotive? We would need two separate models, right? It's not one model, it's two, right? So it's not generalized. Now, one of the nice things about deep learning is that it's more computer science-y than it is data science-y. Okay, so I turned you into data scientists before with the more traditional machine learning. This is different. It doesn't work the same way. It's relies a little more on computer science. These are some open source libraries that are out there. TensorFlow is Google's. And there's many others. But these libraries can be used to create these models. And I don't really have time to explain why it's a little more computer science-y, other than to say, if you have a smart, perseverant developer, which you all do, or you all are, you can download these, go through the samples, and work it, and be more successful with a deep learning model, perhaps, than traditional machine learning. I don't want to make that as an absolute statement, but I'm tired of people saying, data scientists are unicorns, and they're so hard to find, and all that sort of stuff. No, you could get a smart, perseverant developer. Developers are learning new frameworks all the time, whether it's an AI framework, a deep learning framework, or another framework. They can learn it if they persevere and are smart enough to do it. Now, the other building block technology that you may or may not have seen is called knowledge engineering. Now, in the past, this has been called expert systems. And in the 80s, expert systems was a big thing. I worked on expert systems. I got 3 patents for developing an air traffic control expert system. back in the day. That technology, though, is insufficient because what knowledge engineering and expert system does is it scales human experts. So that's where we sit down with you, whoever the expert is, and we create rules about that expertise. That's not a data-driven approach, that's a human approach. That's where we take the knowledge of our experts and we memorialize it in code, in a rules-based system. Now remember what I said about machine learning? It's based upon probabilities. You're going to get false negatives and false positives. So you have a data scientist working on that model, trying to make it more accurate, more accurate, more accurate, but it's not accurate enough. But one expert could come in and say, if this, this, and this, then this. If this, this, and this, then this. So the best way to deploy machine learning models is in combination with expert rules, okay? So a good example of this is advertising models. It's like, oh, we've identified a new market. It's 17-year-olds would love to drink our rum, okay? Well, there's a policy rule that says you better not do that, right? That's an example of a policy rule. So when you have your data scientists, it's that whole hammer and nail thing. Data scientists will work like crazy trying to make that model accurate enough, whereas if they just added a little bit of knowledge engineering into it, they could get the model working much sooner. So we're going to see knowledge engineering and expert systems come back in a big way, but not necessarily alone. So the point is, we always say data-driven. We're at a data-driven conference, but smart humans can also prime the pump, okay? Now there's some problems with this because sometimes experts have cognitive biases. So you have the wrong rules in there or they're biased in some way. So, none of this stuff is, totally straightforward. This is partially how IBM Watson Health works. It uses machine learning to read through corpuses of information, but then it relies on a studio-like tool to have experts help the machine learning, fix the machine learning, right? And that's can be a very successful approach. So I'm not going to go through all the building blocks because we don't have time, but then I wanted to talk to you about how these models, how these AI models or machine learning models make it into applications. Well, when you create applications, just think about it. You get the requirements, and then user experience designers they're blind. They have a blind spot about the predictive models and the machine learning models. So every time you're looking to update a project, you can figure out, is there something I could predict in this application that would make the application better? And then do your data science, see if it works, and then inject machine learning into the application. So the way to think about this is the learned logic. Forget about that for a second. Most applications and software is written by programmed logic. And a programmed logic is just a coder writing the code. No one ever thinks, well, is there some code that could get automatically written by a machine learning model? I don't mean it's writing it, but it's not writing the code, but you're injecting the model and that model's getting smarter over time into that application. So this is how you should, if you want to use AI and you want to use machine learning models or deep learning models, this is how you should think about developing these applications. So these building block technologies can all be used separately or in combination to build intelligence into your application. We recently did I did a wave, because one of the things I do is I evaluate products, and this is our wave on predictive analytics and machine learning solutions. We just put this out. Now you might be saying, hey, where's R, where's Python? Well, it's embedded in some of these. You learned today that IBM in their DSX has a Jupyter notebook. Dataiku is notebook-based, and most of the others are now including notebooks in addition to their drag and drop. So there's plenty of tools out there, and many of these tools are starting to also include deep learning. So what about these folks, because they didn't appear on that wave, right? So Hortonworks, Cloudera, data is essential to this, as we've discussed in the process. If you don't have the right data and if you can't run these algorithms quickly, Google, Microsoft, and Amazon have pre-built models like the voice recognition or the image recognition, And then there's a whole bunch of other players, like datascience.com, Bonsai, BigML, Databricks has their own notebook. There's plenty of solutions out there. Almost all have some combination of commercial and open source. So given the difference between pure AI, which we're not talking about, no one should be talking about it unless you're a science fiction writer, and pragmatic AI, now you can begin to think about how you can inject AI design thinking into your applications. What can you predict in that customer experiences? So these are the use cases that can work today. You can make it do you could potentially make it do any of these things. So the key to all of this is your creativity, because if you can build those apps and those customer experiences that will let you scale beyond 150 friends to millions of friend customers, then you're going to be able to create those hyper-personalized apps. So it's very simple. We do it in a workshop at Forrester with our clients where you walk through a customer journey, your customer journey or a business process, and at every step you say, is there something I could predict here? Is there something I could predict here, or is there some way I could interact with the customer? You'll quickly come up with a list of a dozen things, if not more. And it will really open up the business's mind to what's possible to make those applications smarter. Now, what's the problem with that? Remember what I said? Just because you wished you could predict something with a machine learning model doesn't mean you can, which is why you need a dozen ideas. Because then you're going to have to do data experimentation, and you're going to need a fast data platform to be able to do that. So think about predictive AI, pragmatic AI. AI is definitely your friend if it's pragmatic, but I guess my message is don't let your hopes get too high. It can work now, but it's narrow in scope. So with that, I thank you.